A quick introduction to all of you. I think that Vlad doesn't need any introduction, no introduction, but just in case if his face is unfamiliar, Vlad is one of the Java champions, and he is the #1 guy when it comes to Spring Data, Hibernate, and databases within the Java community. And I think that beyond the Java community, but if you code or develop in Java, then, and if you specifically create any backend applications that need to interact with the database, it's highly likely that you came across some of his articles or took part on some of his training sessions. As for myself, my name is Denis Magda. I'm the head of developer relations at Yugabyte. I've been working with databases and distributed systems for the last 8 years. And prior to the databases, I was on the Oracle and Sun engineering teams building GVM and GDK. So still, I'm very close to the Java community, but right now my interest in the databases. Anything else to add, Vlad, before we get going?
No, I think that we can. Thank you for the introduction. I think we can get it started to don't keep people waiting more than they should. I think I can share my screen, right? So
sure, go ahead.
A second. All right. So, So for today, we are going to talk about distributing data access with Spring Data and YugabyteDB. Now, why we chose this topic is because Spring is extremely popular in the Java world, and Yugabyte is a very useful database which can offer you, as I'm going to show you next, and Denis is going to show you as well. It's offering you a very compelling alternative to what we have been previously using when it comes to database system. I'm going to skip about the introduction because Denis already took part of that, and I wanted to show you something that basically the fact if you're not providing the right data integrity in your application, you might end up facing some some issues that can compromise not just your database but actually your business. And there are actually instances that of companies that basically went bankrupt because of such data integrity issues. Like one example, this is not just theoretical, basically one example is Flexcoin, who used to be a digital crypto, or a digital wallet for cryptocurrencies, for Bitcoin. It was very, it started early in 2014. And in 2014, it went bankrupt. Someone figured out that they are not validating properly the transfers between accounts, and they speculated on it, and they managed to steal all their Bitcoin, 900 Bitcoin. At the time, it was not as much as it is today, but it was enough to basically steal the most of their funds and for them to go bankrupt. So this is one example, but there are many more. Like, for instance, if you are going to search for this, you are going to find even more examples. Poloniex also got hacked around the same time, and they lost 12% of their Bitcoins. And it was the same kind of attack. You know, you have someone figured it out, and they have an issue, and they use multiple simultaneous requests to try to transfer Bitcoins from one account to the other. And because the balances were not properly enforced, and because, as I'm going to show you next, because we don't really have a lot of guarantees in those relational databases we use, they basically, the attacker managed to get more money than they had in the initial account. Sounds very far from like, for instance, when you're reading something like that, it might you might think that that probably won't happen to me. Maybe it's very difficult to replicate something like that, or maybe they were using some NoSQL database, which were very popular around 2014, that at the time didn't provide a lot of guarantees. But actually, I'm going to show you next that it's actually very easy to bump into this issue. The whole logic of doing this transfer is like this. You have to move some money, some cents, let's call it cents, the smallest unit of money, from one account to the other. So the logic is simple. What is the balance in the initial account, in the from account where you are going to withdraw, and from where you are going to withdraw? And if you have enough money, you just withdraw from that account and you add to the destination account. And I have here an example. You can see here an example. I have it in this, it's a public repository, that high performance Java persistence GitHub repository. You will find the example there. And it's a Spring, it's basically a very small Spring test case that tries to emulate exactly this scenario that Flexcoin, Poloniex, or other companies might have went through. And we have two accounts, Alice and Bob. Alice having a sum of 10 and Bob doesn't have anything at the moment. And we have this transfer here. The logic for the transfer, we encapsulated it here. We have a service, it's a transactional, we're reading the balance from the repository, and then we're adding a negative, by adding a negative sum, we're withdrawing from the account and then adding it the same money that we're transferring to the destination account. It's very, very simple. And you can take a look here. We're going to use, initially we're going to use Postgres. And let's try to run this test case that we have here, exactly like it was the context. They were using multiple requests. So let's try to give it a run. And this is going to run now with 16 threads, trying to do this transfer. Exactly the same issue that they were reporting there. And that was written in the postmortem for this attack that happened. And you can see, if you take a look here, you can see that at the end we're just printing the balances, how much Alice and how much Bob are going to have. As you can see, Alice got -5 and Bob got 15. So right from the start, we can see that even if you're using Postgres, it doesn't matter what database, relational database you're using. You can use Postgres, MySQL, Oracle, SQL Server. On all of them, you are going to see this. So like I told you, it's very easy to bump into it. But for instance, just one example. Look what happens if I'm going to switch now the database. I'm going to switch and I'm going to use YugabyteDB, which is a newer database. It's much newer than Postgres, than Oracle. And I'm going to run this on YugabyteDB, and let's see exactly what is going to happen. And this is the default behavior. The default behavior of Postgres, it could be other database, and the default behavior of YugabyteDB. And you can take a look here, Bob got only 10 and Alice got 0. So you cannot get on negative. You cannot basically move more money that you have. And this is the default behavior that we're talking about here. And that's interesting. Let's see what basically happened. The problem that we have here, it's a classical lost update. What happened in a lost update? The problem with this anomaly is that it's not included, it's not mentioned in the standard. You cannot read about it in the database manual. So people tell you whenever there's something that doesn't work, you should read the manual. Even if you read the manual, it will not help you. You still have to know about it. And the fact that it's not documented makes it even harder. So how can you protect or prevent something that it's not even documented, right? But it's so common to get into this kind of issue. So what's a lost update? Lost update means that multiple transactions read a value, and then everyone thinks that they are going to do a modification against the value that they read. But at the moment they are doing the modification, the value has already changed. So here, Alice thinks she's going to withdraw -5 from 5, but in reality, she does that against 0, so she goes into negative balance. So that's basically the problem. And that was not fixed by default by Postgres or Oracle or SQL Server or MySQL, but it's fixed by Yugabyte. So this is a very interesting scenario, and we're going to investigate why is that. So first of all, a little bit of a history lesson here. we've come a long way when it comes to databases. We've really come a long way, because the theory was the code. Basically, he postulated a theory about how relational databases should work and SQL should work, but it was just theory. So IBM tried to put it into practice with System R, so did Postgres. Michael Stonebreaker, who initially worked on Ingress, who is the predecessor of Postgres, he also did that in parallel. But at first, every database worked in two-phase locking, in strict serializability. There was no way to envisioned to bump into these issues. Right at the same time, if you take a look here, Oracle did something interesting. They switched to MVCC, which is something that it's important. We're going to discuss about it next, which gave them an edge. But the thing is that initially all of them were running in two-phase local, which basically is very simple. Every time you're reading, you take a read log. Every time you're writing, you take a write log. And these logs should be released only after you finish your transaction. So you can basically view it here, how it works. When someone, you can basically emulate this even with standard Postgres. When someone does a read, they read with for share. So not only that they read the record, but they take a read log on it. If you take a read log on a record, others can also take a read log on a record. But if you try to upgrade the log to a write one, to an exclusive log, to do a modification, this update will block. And that's important because Alice also locked this record. This update is going to block, waiting for Alice to release the log. So after commit, Alice releases the log. And now Bob update can proceed. He does the update, but before he does the update, he acquires an exclusive log. And if Alice starts a new transaction and wants to read, taking a read log, apply a read log on the record, she will block until Bob releases that log. So that's exactly how two-phase locking used to work. It's very simple. It provides you with strict serializability, but it really doesn't scale. If that was the problem, that's why all databases moved on from two-phase locking eventually to MVCC. That's basically the story. Also, when two-phase locking was first used or introduced into applications, the challenges were very different than what we have today. There were terminals, mainframes, and only 100 active transactions. I mean, this is just tiny compared to internet and the amount of traffic we have nowadays. So some databases take a very smart move, like Oracle. They introduced MVCC since 1984, which, because it provided better performance, allowed them to get a lot of market share. Even today, it's one of the most popular or most widely deployed database among companies. Oracle did that move to MVCC 30 years ago. Other databases did the same. Postgres uses MVCC. MySQL InnoDB uses MVCC. You can also have it in a SQL server. But what it means that now we don't take read logs. So readers, when I read something, I'm not going to block others from writing. And when someone writes, it's not going to block others from reading. So even if you take an exclusive log in a relational database, you're not going to block others from reading. That's how it works. You can see it in action in Postgres, how it works. When you're inserting a record, and the table also has this xmin column that marks the transaction who made the modification. And until you commit, you can read the record, others cannot see it until you commit. So the database plays with this visibility. When you're doing a delete is basically just a soft delete. You just mark the xmax column with the transaction ID. Until you commit, if you did a delete and before you commit, if you do the select against this record, the database will hide it from you. Others can still see it until you commit, but afterward, they're not going to see it. And the update is just a delete followed by an insert. And right at this moment, if you select this record, you are going to see the latest version that you created yourself, and others are going to see the latest one. That's why MVCC allows you for instance, that's why it increases performance because you don't no longer have to take logs, because you can operate with multiple versions on the same time. So this is the principle between how most of these databases operate. And why it's important? It's important because two-phase locking basically could only generate these issues. But nowadays, in reality, we have more, like the one that we bumped into. The standard only tells you that you can have dirty read, non-repeatable read, and phantom read, which are basically in relation to the fact that you can take or you cannot take these read logs. For instance, the dirty read tells you something like that. If you make a modification and others are allowed to read uncommitted data, why they could read uncommitted data? Because this select would not take a read log that would have blocked against this exclusive log. So if you can do that, what could happen? The other transaction can roll back, and now you are going to use a value that's no longer to be found in the read log, taking a decision based on something that was transient. Non-repeatable read means that you read a value, someone changes it, commits, and if you reread it again, you read a modified value. So in between two reads, someone made modifications. So you cannot, maybe you took some decisions here that are no longer true. And phantom read basically is just like the previous use case, but now it spans over. So your select doesn't return only a record, it returns a range of records, like all the comments of a post. You read all the comments of a post, there are 3, someone inserts another one, now you get 4. Why would happen this? Because your reads would not take a predicate log. So most of them were associated with the fact or how that read log acquisition would be taken. But that's just, and the standard, and nowadays the manuals only tell you that, but that's not sufficient. In reality, you have more anomalies that your application can suffer from. Read skew, which can happen if you have 2 records. Let's say that we have 2 records with a one-to-one table association. Every time I'm writing the post, I have to mark down who made the modification. So Alice reads the post with the title transaction, now follows Bob, who makes a modification. He changes the title of the post, and of course the updated by column in post details is updated, marking the fact that Bob made the modification. And now when Alice resumes and she reads the post details, she's going to read the value of updated by Bob. So she, in her transaction, she has this combination. The post with the title transaction was written by Bob, which this combination never existed because now the reads span in this transaction span with the states of two database consistent states, but different states, not the same state. Write skew. Write skew basically starts from the same context, but now one transaction modifies a single record and the other modifies the other record. Both are allowed to commit, but they break the consistency in between them. Why would this have happened? If this is Hibernate, and let's say that Bob wanted to make this modification, he would modify both the post and the post details as entities, but only the post would go through because the dirty checking mechanism would just disallow the update on post details to happen. So he would update only the post. Now, in the case of Alice, it could be something like that. She could have run a merge, and the merge basically does the select first. And for instance, if the post hasn't changed against what's in the database, the update would not go through, but the post details update would go through. So both of them, now in the case of Bob, he would think that he leaves the database in this state, and Alice would basically wanted to keep it as post with the title transaction updated by Alice, but the combination in the end is going to be a mix of what they would have expected. And the last update is the one that I showed you that was generated this transfer issue that we had before. In between, at the moment when I'm doing my modification, someone already has modified the record, and now the state is no longer the one that I read. So in reality, you have many more anomalies, and the isolation level controls how these anomalies are going to be prevented or not. And the standard is very simple. It tells you this. You can read about it everywhere, and in the standard on the database manual, telling you that you have these isolation levels, and this is the relationship between the isolation levels and these the only issues mentioned by the standard. You can see here, there's no lost update because it's not mentioned. But in reality, things are different. This is Postgres, for instance. In Postgres, you have all these 4 isolation levels. Read uncommitted is just an alias for read committed, so it doesn't really exist in reality. It's just like a reference to read committed. You cannot have dirty reads. Repeatable read is basically snapshot isolation, and serializable is serializable snapshot isolation. So you can see even from the start it differs from what the standard would normally tell you. Yugabyte, in this case, you can see here, by default in Yugabyte, the default isolation level is snapshot isolation. And that's why when we switch to Yugabyte, we didn't have that issue. The lost update was prevented. This is very interesting. By default, Yugabyte uses a more strict isolation level that, as you can see here, it prevents a lot of issues. Only the write skew is allowed to happen. But then you can switch to serializable, just like in Postgres, and then you can prevent that as well. You also have in Yugabyte the possibility of getting a read committed isolation level, but you have to enable it when, for instance, you start Yugabyte. For instance, in my case, I'm starting it in a Docker container. But if you have it running on in the cloud, you would have to enable it like this, and then you can also have read committed, just like PostgreSQL does. But you should know that that's going to be an isolation level that provides less guarantees than what by default Yugabyte gives you. And that's interesting. It's not just Yugabyte, other newer databases provide these guarantees as well. Now, the trend is that more databases that emerge now provide a stricter isolation level than what we used to have before. And that's, for us as developer, I think that's good. That's very good. Another thing which is also worth mentioning.
Vlad, what if we just take a little pause here?
Yeah, sure.
Just
sure,
to make it, like for me as an attendee of this training session as well, I want to make my short summary on what you have just showed and how that summary might be useful for us, for the application developers. And also, if you allow me, just a quick 2-minute introduction to Yugabyte, because I guess that some of the guys and ladies who are visiting us today, they might not know like what YugabyteDB is. So my summary actually, folks, that test that failed with PostgreSQL but succeeded with YugabyteDB. First, it doesn't mean that Postgres is screwed. Postgres can, with Postgres, you can prevent this anomaly, but you need to switch to another isolation level, right? You have to mark your transactions as repeatable reads. And the second summary, you need to know that, like when you select, most of the times we use ORMs, right? You can be sitting on Spring Data, Micronaut, or something else, and then you just switch to your database and you think that you're in good hands. But when you write your business code, the database, read committed is a valid isolation level. But Postgres doesn't know if that isolation level is valid for your business transaction, for your business operation. That business operation that Vlad showed you when, let's say, someone was transferring funds from one account to another. No, such an operation has to use repeatable read at least, and not the read committed one. And for you, the outcome here is just know your database, know what's your default isolation level, and make the right choices, right, based on your business transactions. Because read committed is enabled in Postgres and many other databases for good reason. It's kind of much more concurrent, right? Because what Vlad is going to talk about next is just different types of logs, right? Row level logs and column logs. But in YugabyteDB, in the distributed database, we switched to the repeatable read by default, and that's why you didn't have that anomaly in the test in the beginning, because we use a little bit different way for locking your records whenever you need to change something. And this is what Vlad will show you. But right now, talking about Yugabyte, right? Because we mentioned this word many times. Vlad, let me quickly
sure, please
take the screen.
Yeah, sure. I'm going to stop the share.
Yep. Yes, that's a wonderful, actually, test to start with. It's like everyone can wake up really quick if you see like that something fails with one database and works by default with another.
Yeah.
And by the way, folks, ask questions if you have any questions. If anything is not clear, if you want us to deep dive into anything, just use the Q&A toolbox in Zoom. So what YugabyteDB is? YugabyteDB is a distributed database. Basically, you can run it across multiple nodes, across multiple machines, across multiple cloud regions, and the data will be sharded. Multiple machines will be storing copies of the data, and if any node goes down, you will be able to keep running because the copies of your data will be available on other nodes. That's the beauty of distributed databases. They share the workload, they distribute the data, and they come with more advanced fault tolerance capabilities. From the
Denis,
internals,
it says loading on the screen. Can you see the can you see the view? Because I only see loading on the screen.
Seriously, that's
yes,
fun.
Yes, so you okay? Now it works. It works.
How about now?
Oh,
still loading?
No, yes, still loading.
All right. So I know one trick. Let me do this. I know one trick. There is actually a all right, now let's make it simpler. The old way. So it looks like that. Yeah, Zoom doesn't want to show my stuff. Anyway, so just 2 slides. So from the internals perspective, as a distributed database, YugabyteDB is comprised of 2 components, the compute or query layer and the storage layer. The compute query layer is built on PostgreSQL. We basically took the PostgreSQL source code. We are built on the PostgreSQL source code. You can think of YugabyteDB as a fork of Postgres, and we enhance that source code. But generally, whenever your application connects to YugabyteDB, it will treat YugabyteDB as Postgres. We are runtime compatible with PostgreSQL. But this is where the similarity ends. The beauty of that similarity is that you're getting most of the Postgres capabilities out of the box in YugabyteDB. But where the similarity ends is YugabyteDB distributed storage layer. Our storage is different. Postgres stores data in a tabular format. It uses B+3 indexes. It uses the row level logging that Vlad is going to describe next. While YugabyteDB is distributed, our storage can span across multiple nodes. The data is located across several machines. We support sharding of the data automatically. We run distributed transactions. Whenever your transaction updates in your record, the update usually copy of the record is usually stored at least on 3 machines or 3 nodes. And we synchronize changes via the Raft consensus protocol, making sure that in case of any outages or network blicks, you don't get any data inconsistencies. And this storage is actually inspired by Google Spanner. Google Spanner was one of the first true distributed relational databases, SQL databases that supported transactions. And we looked both at Postgres and Spanner, and we decided to create YugabyteDB, which is open source. If you take a closer look at the query layer or compute layer of Postgres, of YugabyteDB, sorry, it comes with the same components that you will find in the open source PostgreSQL. The postmaster that accepts your initial application requests, the rewriter, optimizer, planner, executor, all of those components of Postgres present in YugabyteDB because we're built on the source code. But some of the components such as optimizer, planner, and executor, they are enhanced because those components, they have to be aware of our distributed storage layer. And we just, enhance them and adding some optimizations and some logic that will take your query and distribute and run this query across multiple nodes in your network, right? So that's a quick introduction. As for the questions, let me quickly check one. Ranganath asking, I'm using MySQLDB and Redis and writing the transactions using Atomica's JTA. The application is based on Spring Boot. Our application is a peer-to-peer lending platform, and we need data to be stored in JSON, NoSQL, RDBS. How will the Yugabyte be beneficial for us? So as a quick answer for you, YugabyteDB supports JSON. JSON support was added to Postgres a long time ago, and we support it officially. It's a very sophisticated support. As for the NoSQL, I mean, for me, like YugabyteDB belongs to the category of distributed SQL databases. And if to explain quickly what a distributed SQL is the NoSQL that can scale, that can run distributed transactions. So you are getting the scalability characteristics of typical NoSQL databases, but you can run your SQL requests and you can run your SQL transactions. You can work with JSON, etc. So think about YugabyteDB as a distributed relational database. Another question, is it hard fork of Postgres, or are you going to be synced with the upcoming new features and versions? So right now, presently, I think that what we have in production, we use the fork of Postgres 11, and we are actively working on Postgres, on switching to the Postgres 13th. And this work will continue like endlessly. So whenever the new version of Postgres comes, we are putting this in work, and our goal is to switch to the new level, to the next version. But it's like slower than, let's say, with Amazon Aurora, because Amazon Aurora is basically what? Amazon Aurora is not a true distributed database. Aurora scales reads with the read replicas, but all the writes come to a single node, single writer in Aurora.
Exactly.
In YugabyteDB, it's completely different storage. That's why when it comes to YugabyteDB, it takes more time for us, let's say, to upgrade from one Postgres version to another. So Vlad, the next question probably goes to you, and then I will switch over the mic and screen to you as well. So what's the difference between serializable isolation level between Postgres and Yugabyte, and how Yugabyte solves Postgres problems like dirty reads on the same isolation level on which Postgres had them?
All right, so the difference is between how they treat the exclusive logs when doing the writes. I'm going to show you next about it, but before we do that, so I'm going to go to the answered one related to JSON. I also have a part where we're going to talk about JSON, so you are going to see, so Rangana, you are going to see that we're going to cover that as well. Now, before I'm going to continue my slide, so let me first share my screen. Exactly like Denis told you, and this is also relevant to the question that we're having here, and Denis also marked it out. Even let's say that I'm switching back, so now I'm switching to Postgres, right? But by default in Postgres, we are using just the default isolation level, and when using the default isolation level, which is read committed in Postgres, like Denis said, for very good reasons, because it scales better. Most databases use that. The only difference is that MySQL switches to uses repeatable read, but the other ones, SQL Server, Oracle, Postgres use read committed by default. So here it didn't work. But just like Denis told you, we can also do that. This is Spring, so this is probably very familiar to most of you. You can do something like that, repeatable read. And now we're doing a repeatable read, which is basically snapshot isolation in Postgres. And it's going to fix this issue, just like Yugabyte fixes this issue, because this snapshot isolation, this repeatable read, the guarantees offered by the repeatable read in Postgres and in YugabyteDB are the same. So the lost update is going to be fixed. But there's a difference. They're not, so in terms of guarantees, they are the same. But there is, the difference comes in the implementation that they are using. For instance, for every, not just for Postgres, for every relational database, Oracle, MySQL, SQL Server, and of course, Postgres, all these top relational databases, the flow goes like this. Every time you're doing an update, every time you're doing a delete, that delete goes and takes an exclusive log. Why it happens like that? Because basically you have a single representation of the record in the buffer pool, and you cannot have two transactions modify the same record at the same time. If you had that, you wouldn't have atomicity. So you need to do that. So the relational databases have to do that. They take an exclusive log. That means that in the same time, if you have a different transaction, a concurrent transaction trying to update the very same record, you see, it's the book with the ID of 1. It's the very same record. And the other transaction tries to do the same. What will happen? They will block. What blocks? It's the lock acquisition that blocks. So Postgres works like that, MySQL works like that, Oracle, SQL Server, all these databases that maybe you're using, maybe you've been using, they work like that. But not Yugabyte. YugabyteDB works differently because the lock is not taking on the record, the lock is taken on the column actually. So for instance, if I'm doing something like that, update the book, but I'm going to update this column, only this column is going to be blocked. And other transactions in parallel, they can concurrently update a different column without blocking and still using snapshot isolation. So not only that, for instance, even if you're using repeatable read isolation level, it can happen that the updates scale better because previously they would have blocked. So MVCC solved one problem. It allowed for reads to it allowed reads to not acquire those read locks when they execute. Like the selects don't need to acquire those read acquisition requests. But then Yugabyte takes this MVCC way further because it doesn't take exclusive locks on the record when it applies modification. It takes it on the column, make it more granular, enhancing even more the concurrency of your application. So it's a very interesting approach. No other MVCC database implementation that I'm aware of has something of that, at least among the top relational databases, which I'm also, maybe like you, are more familiar with. But there's a catch here. If you want to enable this behavior, and if you're using Spring Data JPA and Hibernate, there's one thing you have to do. You have to use dynamic update. You have to use this annotation that comes from Hibernate, which allows Hibernate to generate these updates dynamically and to include only the columns that you have modified, because otherwise by default Hibernate would basically include all the columns of the entity that you're modifying. Why? To increase the likelihood of statement caching, and that's the behavior. And actually, that's the behavior that they've been using, and to cache the statement that updates the record. Now, before I'm going to do next, I see that there's a question on the slides where the Yugabyte isolation levels are shown. They are different. Why is that? 1 second to go back. Let me go back here. So this is with the default isolation level, and this is actually, if it's not the default here, I should have changed the title for that. This is the default, and this is Postgres. So basically, in terms of repeatable read, nothing has changed. The third row here. Now, by default in Yugabyte, all these basically are just aliases for repeatable read, just like in Postgres, read uncommitted is an alias for read committed. That's why they are like this, because by default, all these are aliases. By default, you don't really have a read committed. By default, the minimum isolation level is repeatable read. There's nothing below that in Yugabyte. But you can take a read committed. So here I should have changed this to let's say lower isolation level or something like that to make it more relevant. So here you can switch if you really want to read committed. Why would you really want to do that? If you're using read committed, then Yugabyte is going to work like Postgres. It's going to take the row level locks, not column level locks. That's a very important distinction. You have to think about it. So
yeah,
let me know.
Here is also about read committed. I mean, the read committed support was added to Yugabyte a couple of months ago, and we did this from the compatibility perspective. As folks, what we're showing you today, the default, like whenever you create an application for Postgres or Oracle, for most of their business and application requests, you're going to use the default isolation level. But then when you, let's say, switch to YugabyteDB, where the repeatable read is enabled by default for a good reason, some of those business application requests might start failing, because if, let's say, you run 2 transactions with the repeatable read isolation level, if there is a conflict, then one of the transactions will fail. So you might start getting different exceptions in your Java code that you have never seen before at Postgres, because Postgres uses read committed, which is a different approach. And to YugabyteDB, we added exactly for that, because a lot of the code was already written for Postgres, and that code was designed and used for the read committed isolation level. And when someone migrates an existing Postgres application to YugabyteDB, we don't want you to have a lot of surprises with application runtime level exceptions because like of the conflict generated by repeatable read transactions. But this will allow many developers to migrate easily. But then again, we usually advise to review the logic and consider switching to repeatable read whenever appropriate. And actually, Vlad, the other day I was sitting and thinking, like, why, for instance, distributed databases like YugabyteDB decided to implement column level locking and not, let's say, row level locking, because it would be simpler. There is already the knowledge, right, the practice and the papers around that. But with distributed, like, take this example. You have a single node database, let it be Oracle or MySQL. And an application request just needs to get from the application side to the database, and then the database will execute it as fast as possible because all the data is on this node. With distributed databases, that's not the case. Your application sends a request to the distributed database cluster, and then that transaction can span across multiple nodes, etc. Which means that the network latency can add up, right? The network, all of those distributed databases, they already have to accept this network latency. And they are looking for the ways on how to optimize the execution of concurrent transactions. And the column level locking is the way how YugabyteDB as a distributed database found the way to improve the latency and performance of your transactions, because already most of the transactions will be running across multiple nodes where the network latency will impact you, right? And we don't want, let's say, to impact your latency further with row level locking. That's why we wanted to use the column level locking. All right. So what else? We have another question. If we make a change to YugabyteDB from Postgres, will we see the performance degradation in the throughput because of the isolation level change? Do you have any performance benchmarks? I mean, it all depends on your application. It all depends. My advice is as follows. The migration is usually straightforward, but then do the performance testing and load testing. We certainly come with a list of best practices when it comes not only to Yugabyte, but to distributed SQL databases in general. Only one important remark. Don't try to kind of compare a single node YugabyteDB cluster to a single node Postgres instance, because that's not a true and real use case. Nobody uses YugabyteDB in production in a single node configuration. So that's why when you try and when you test, deploy a multi-node YugabyteDB cluster and see how like it helps you from the scalability and performance standpoint. And if you need any assistance with performance tuning or benchmarking, we have an open source Slack channel. Just join it and send us a note.
Yes, and also those benchmarks against databases, against some, let's say, load that it's not even what you have in your application, they are irrelevant, actually. I've seen it with frameworks, data access framework. People used to compare like Hibernate against Eclipse Link or Spring against Quarkus, but most of the time those don't make any sense, actually. In reality, the only thing that matters is your own application, your own business logic, how you're using it. Everything else is just, I would say, it's not relevant, actually. And if you want performance, because people say, I need to switch to this to get performance. No, if you need performance, you do performance tuning, actually. That's how you address performance issues. You do performance tuning, and you can do performance tuning with any database. And with any database, it's not like you have, if I have performance issues, I have to switch the database. No, basically, when you switch the database, you switch because you want to take advantage of many things, because this database that you want to switch to fits perfectly into the kind of architecture that the business requirement demands, because in reality, the technical solution that we're giving is not an island. Basically, it comes to serve something in the real world, the flow of the business that basically enables or requires this technical solution. So it's something like that. That's why, and when you see those benchmarks, always take them with a with a little bit skeptical about it. And the ones that you should trust are your own tests. You can do your own tests, just like I've done here in this repository. You can always run your own tests, which are going to be more meaningful to you anyway. There's some random test over the internet.
Mm-hmm. And also,
right.
just a good remark.
Yeah.
I mean, if you're already happy with Postgres or your other relational database, you don't have any performance complaints, you don't need to switch to YugabyteDB. You switch to YugabyteDB when you outgrow the capacity of your database server. For instance, you cannot longer scale vertically, you have to scale horizontally. This is that's the first case when you need to migrate from Postgres to YugabyteDB. The second one is fault tolerance. For instance, you are deploying your Postgres right now in the cloud, right? And you heard about those outages. Availability zone went down, another region is unavailable for multiple hours. I mean, like, I live in the East Coast, and it happens all the times, like when one of the Amazon regions goes down. And if you want your database to stay available, even during zone or region level outages, this is when you switch to YugabyteDB, right? When you want to get advanced outage. And certainly, once you do this, performance-wise, at least it's going to be comparable, if not more, because you can always scale out your cluster. So keep this in mind. So the last question, Vlad, and then we can move forward. Let me quickly answer it. What's the use of row and column level logs when using MVCC? What Vlad showed you with MVCC, you still have your update requests, right? You need to update data, you need to insert the data. Whenever you need to update a record, you need to put logs. Otherwise, you would get dirty writes. So that's why you need to have logs even for the MVCC. They're required.
Yes, because otherwise, if you don't take these logs against this architecture of most relational databases, which use a single page in the buffer pool, where basically that represents the record itself, where the record is, there's only one representation. If you don't take those logs, then basically you wouldn't be able to know when you do a rollback, what is the consistent state which I'm actually rolling back to. That's why you need to take those logs. It's basically to have a proper serializable in the end redo log that it's linearizable. Otherwise, without having this, you would compromise atomicity. That's why they take. But then how does Yugabyte manage to run it? Because they basically do this check, just like in MVCC, you do the checks, basically the transaction engine does the checks and figures out that you interleave reads and write, and you have lost updates, read skews, or other anomalies. In the same way, it basically detects these dirty writes optimistically. That's how it works in Yugabyte. So basically, the conflict would be allowed to happen, but it will be detected by the transaction that tries to is basically follow. So it's like in any optimistic locking scenario approach. It's the same thing. So like Denis told you, the reason why read committed was added was to make this the experience, or when you switch to Yugabyte, to be closer to what you have experienced. Even this for these logs. That's why basically by taking these logs, you basically prevent some anomalies to happen, because otherwise, if they are going to be allowed to happen, you are going to see more optimistic failures in your application, which you should cover, because otherwise the user is not going to have a nice experience getting a failure on their screen. Okay, and one of the last things that I have, and then I can leave it to Denis, is the fact that and this is relevant to the first question. The thing is that in relational databases nowadays, even in the standard, we have support for JSON. Now you don't really have to add MongoDB to your architecture just to have JSON. You already have it in relational databases, and you also have it in YugabyteDB. So where would that be useful? For instance, one use case of JSON is, for instance, if you want to create an audit log, and you can create such an audit log and store the old and the new state of the records in JSON columns. How you can do that? In this repository that I told you about, this high performance Java persistence repository, it's basically on GitHub, and there you can have something like Yugabyte and audit log. This is a test case here. You can see here it uses Yugabyte, and what we're doing, we're creating a generic audit log. We can use it even for all the columns, for all the tables that we have in our system. And every time we're making modification to the tables that we're interested in, we're going to insert into this audit log what we have done, when we did an insert, when we did an update, when we did a delete, and for the tables that we're interested in. And you can run this test case, and you're going to see it's going to work like in it's going to work in the same way like in Postgres. It's going to work like in Yugabyte in the same way. So you have support for JSON, and more than that, because of the architecture of Yugabyte, you can benefit from the fact that you can shard this audit log, or because this one is the kind of structure that is going to grow in time, and you'll have to have some plan about partitioning or sharding it, because otherwise it's going to take quite a lot of space. But the architecture of these distributed databases can better address this requirement than traditional relational databases, where you'd have to use archiving, partitioning, or sharding manually. And that's not really an easy task. You can basically see it here. When we're inserting, so 1 second to see if I have configured here the database. I have some Postgres, but let me connect to Yugabyte here, default schema. All right, let's do it like this. Another option, 1 second, properties. Yugabyte, the port is fine. Schema should be default schema, like that. Let's see if it refreshes it. Otherwise, we can do a pgadmin. Yeah, I think that I need to. I think that I'm using an older version of.
What are you trying to do? You created your own.
I'm trying to connect
database.
to. Yeah, basically, I'm not sure if it works from this from the database visualizer here. Actually, maybe it could work from this one from Postgres, but I have it. It's much simpler if I'm connecting to pgadmin. That's one more thing that it's nice. You can connect with pgadmin with all these tools to both Yugabyte and Postgres. It works in the same way. So what we're trying to see here, we're trying to take a look at our tables. That's basically what I'm interested in. So I have this audit log table that I want to see how it works, how I'm inserting data into it. So this is where the data of the audit log will, and I'm creating a book and maybe an author there as well. In the beginning, I don't have anything, so I'm creating an author. And I'm creating a book. And let me jump here so that those transactions can run. We can see here in the console what has happened. We did an insert into author. We did an insert into book. So we can go here and recheck and see that, yeah, we created a book. And we also have, and in this audit log, we have the author, the book entries, and this is the record in JSON that was created. So we encapsulate it as JSON. This is much more convenient than using the standard approaches where you duplicate all the columns. If you do that, you would have to create a different table for distinct audit log tables, table for each table that you're targeting. But with this, you can even have a unified solution. And the same works for when you're doing modifications. So let's say that we're applying some modifications, some updates to those. You can see I'm changing the author, I'm changing also the book. So some updates are going to be generated this time. We can see here, we run some updates. And if we go back here and we refresh, we're going to see that audit logs are going to be added here as well. So we're going to see that, you see, we have the old row and the new row in here as well. So that's going to be convenient. So again, this maybe answers the first question about JSON. You have it in relational and nowadays in distributed SQL databases as well. I think this is a very nice thing that we have. And one thing that in my case I cannot show you, but maybe Denis can better show you, because I'm running Yugabyte on Docker. I'm not running it on cloud. Basically, you can distribute. This one can be distributed. The audit log. It's not like in traditional relational databases where you have your table and it either stores some pages in the buffer pool and everything else is stored on the disk because it doesn't fit into the buffer pool. Basically, you can distribute it into multiple nodes, and then it's during the query assembles from different shards, and then you get your result. But I think that Denis can better show you or talk to you about that part. So I'm going to
yeah, let's continue.
pass the microphone.
I think that you did a pretty good job by loading us with the
Thank you very
concurrency and JSON related ideas. I mean, the concurrency one, it was probably the most hardcore beginning of the training that I've ever attended. Usually such a section comes somewhere in the end so that people can wake up. But I think that was an excellent beginning, because it was straight to the point that, guys, we're going to talk about some internal, sometimes unpleasant stuff, sometimes easy to understand, hard to understand, but it's very important. Because what matters most to the companies, we can create all those fun applications, right, microservices, but the data, consistency of the data is the most important to the business. Because if you compromise data, you will compromise your customers, and you can get out of the business. What happened to those two companies, right? Exactly. Whose application developers basically use read committed instead of repeatable read for some of the business operations. And again, it doesn't mean that you have to switch from read committed to repeatable at all, right? You just need to select what business requests have to use repeatable read, because some of the even some of the business requests have to use serializable transaction if you want to get rid of the writes queue that Vlad showed you. Anyway, YugabyteDB, right? It's shared, it is distributed. Let's break it a little bit. I want to do what I want to do right now. I'm not going to show you any slides. I came unprepared for purpose, but we're going to code a little bit. What we'll do, we'll start a 3-node YugabyteDB cluster. Let me copy that command. I can't remember it, folks, so forgive me. And you would not remember it as well. So I also use Docker, but I will start 3 nodes on my local Docker machine. So let's see that they are running, and let me make the font size a little bit bigger. And you don't want to see this, right? Let's customize it a little bit. So it sounds like the database is started, at least it's up 24 seconds ago. And I'll use this UI. So what I have here, this UI shows me the state of the cluster. Okay, I've got 3 master nodes. The master nodes, we have 2 types of nodes in YugabyteDB. The master ones that basically store their cluster-wise metadata. They accept different DDL statements and execute them and do all of the management-related stuff. But all the data is stored on T servers. Think about T servers as your dedicated YugabyteDB nodes that keep your data, and they process your requests and your transactions. So we also have 3 T servers on my local machine. So right now we don't have any tables except for the system different tables, the tables from their Postgres system catalog. But we're gonna fix this soon. No any load as well, no any read or write operation. This one I think is some bug. I think that we just made a conversion from some number. But anyway, it's 0 here as well. So my application, it's a trivial market orders application. What this application does, it connects to a remote service somewhere in the internet, and that service generates fake market data. Some people buy and sell different stocks. I'm going to subscribe to that stream of data and put all those changes into all those market orders into the Dockerized YugabyteDB instance. So my application is as follows. It's just a Java application, nothing new, nothing exciting. I don't even want to show you the source code. It's boring. The application, I will start using this command, also in Docker. So what the application does, the most interesting part here, it connects to my Yugabyte cluster using this properties file. And this properties file uses the standard Postgres JDBC driver. We are not using anything from YugabyteDB yet. We just use YugabyteDB, but we continue using the driver that is developed by the PostgreSQL community. I'm connecting to this YugabyteDB node. That's their host name of this node within the Docker network, the port, and the passwords that are hard to break. So let me see right now. The application connected successfully. It created the tables, and right now I've got the first trades coming. So the trades are being streamed from the internet, from the public internet, and we've got some folks buy Google, Apple. Probably right now that's a good time to buy those stocks. Okay, now the interesting part. Let's go back to my UI screen. So here is right now you see the load, folks. We've created the table, and every node in YugabyteDB handles both reads and write requests coming from this application. And this is expected because the data is distributed. Let's say that some stock, some purchase is stored, the primary copy of the purchase is stored on this node, but the backup copies of this purchase will be stored on 2 other nodes. By default, we use replication factor 3. So when the update comes to this node, the change will be synchronously replicated through the REF protocol to other nodes. And if you take other records that are being placed in this database, one node will be the primary for this record, the other node will be backup node for another record. So it's just that's how the data gets sharded. So now let's talk about fault tolerant and let's talk about outages. So what I have, let me open another terminal. So I have, let me stop one of their YugabyteDB nodes, for instance, the first one. And this is how I'm going to emulate the outage. I will stop this node and even I will go forward and I will remove this altogether. It's removed, it's no longer there. So what happens to the application? Application is stopped. Why? Because this application, I just made a mistake. I stopped the application, I stopped the node the application was connected to, right? I used the standard PostgreSQL driver. The application is stopped, and certainly, so what to do right now? I have to reconnect to a different node because nothing happened to the cluster. This cluster is as healthy as the wolf, you see? So this node is no longer responding. So soon we will see that this node is kicked off from the cluster. This one, the first one. Let me make the font size bigger. So it's no longer responds to the heartbeats, but the other 2 nodes are alive. All the data is here, all the data is consistent. And if application found a way how to connect to all of the nodes, the application would not be impacted as well. But right now, yeah, you see that the cluster detected that this node is out and it's considered as dead. By default, we take 60 seconds. The cluster waits 60 seconds by default because you might be, just going through a maintenance window. You're restarting and upgrading the node. But You can change this number, but by default, 60 seconds are given to a node to return to the cluster. So the node has not returned. So now let's do this. Let's return this node, and I am specifically purposefully restarting it from scratch. I don't want it to keep any data. Let's say that it was dead, the cloud region went down. So right now I am returning this node. I'm giving this node the same name. And let's see what happens. It joined the cluster. It doesn't have any load. Nobody actually does any load. It doesn't have any load. But generally, yes, it's going to become a primary node for some of the tablets. A tablet, think about a tablet as a shard. Shard, like one of the shards that keeps your data in the cluster. So what I think I also need to do is to restart this application. So Docker start market orders instance, because it's another, it doesn't handle reconnects. What I forgot to do, let me do this. Docker stop market orders. I want to print the logs, and we will start it differently. We need to add this parameter attach. So right now the table is already created. We connected because the node is back. I returned. And the cluster is up and running as it was before. We returned the node, we are getting the new traits, and we are putting the traits in the cluster, all right? So generally what I showed you, the cluster is alive. I simulated a node outage, but everything was fine. After that outage with the cluster, the data was not kind of lost. It was not destroyed or anything like that, but the application was impacted. The application used the standard PostgreSQL driver to connect to the database, and that driver uses just one connection endpoint, and that connection endpoint, evaporated thanks to my actions. How can we fix it? Because in YugabyteDB, we aware that our cluster is a multi-node one, and we created a fork of the PostgreSQL driver, and that fork is the cluster aware. So let's switch to that deployment. For that, I will remove, let me stop this market orders application once again, and let me remove this container. And the next, when I will start this application next time, I'm going to use the same command, also in Docker, but with one difference. I'm going to use this connection properties file. And let me show you what's in that file. So the difference of that file, I'm also connecting to the same node that can go down, but right now I'm using the YugabyteDB's version of the driver. It's called YugabyteDB cluster-aware data source. So what it does, so right now when my application connects to the cluster via this node, the driver will learn about other nodes that exist and that can accept my requests. And then the driver, when the driver will be creating all of those connections, it will be load balancing the application request. It will automatically connect to not only to node number 1, but node number 2 and node number 3. So this is what happens transparently for us. So let's check that actually, yes, we managed to connect with this driver. So here is, I also don't expect any changes. Yes, I see the read and write load across the cluster. And now let's do the same experiment. I like to break things. So we are going to the, we are going here. And what we want to do, we want to stop Docker stop YugabyteDB node 1, the node my application is connected to. And let me also just remove this container for the future. So I stopped it right now. So the application, it's some of the connections will fail, but the connections that were to that node, to the stopped one, they will fail. And the driver, the pool, it will reconnect to the other nodes. So generally you see that that node is down, but the application keeps running. Why? Because nothing happened to the cluster, except that the cluster lost one of the nodes. You see the node is still kind of the status alive, but it's not alive. The cluster just waits for that 60 seconds period timeout. That is the default one. But we have the load. You see the load is here on those nodes. This one don't pay attention to. It's just not refreshed. It's static. But these two nodes, they continue processing my reads and writes. No any inconsistencies. Nothing like that. The application keeps running. So let's see. Yeah, this node is dead. So how about our application? The application, all is good. All is good. So this is how, I mean, the same use case, but right now we did another improvement on the application side. The cluster is fault tolerant, it is distributed by default. In the first test case, in the second, I stopped the node and the cluster was not impacted. No any data was lost. But in the first case, my application was impacted because it used the standard driver and the driver was not aware about other connection endpoints. But with the second scenario, the driver is aware, uses a different driver, different data source, and the data source automatically collects IP addresses of the nodes that are in the cluster, okay? And it does this dynamically. Suppose that you stop or remove nodes, the driver will learn this information and you will be able to use connections to many endpoints. So now what else? Let's return this node back to the cluster. No any changes again to their application. The application works as it used to before, but I just, you know, restored the number of the nodes in the cluster. I want to have at least 3 nodes so that the replication factor 3 is not impacted. So that's how you can, you know, quickly test and the fault tolerance with YugabyteDB using Docker, whatever you have near your hands. Certainly, you can easily replicate this demo and these usage scenarios, these fault tolerance scenarios to real public cloud environments. The only one difference would be that it will be running somewhere in the cloud and the name of the cloud region and zone would be completely different. Any questions or anything from your end, Vlad, if you want to add on anything?
No, I think that that was a very nice presentation. I like the fact how it managed to connect automatically, because that's basically that's basically a problem that you might have if you're using if you're connecting to or if you have a proxy that connects, to be able to connect and to fall back automatically. That's going to be very, very useful. Otherwise, you just end up having that application being stuck to some node that can probably is not going to come up, and the user who connect to that node are going to experience this problem. So it's very nice that it has this fault tolerance. So I think that it's going to be very, very useful for who is going to use it. So not only that. So yes, by default, you can start using the Postgres driver, but if you're using Yugabyte, I think that it's worth using the Yugabyte enhanced driver. Otherwise, you lose this. You're going to lose these optimizations. So that one is nice to start with.
Exactly. I mean, you certainly can reinvent the wheel and implement this behavior yourself with the standard driver, but most likely we have, you know, we know how to spend our time, right? And don't want to spend this time on. And just in case, this driver again is, as long as that's a fork of the Postgres standard driver, for you is just drop in a replacement. You just whatever you use, Maven, Gradle, you switch from one version of the driver to another, and in YugabyteDB, DB's version of the driver, you just have some additional configuration options if you need them.
And one more question, because this is basically relevant to anyone who nowadays is using a relational database where you have replication, you have, just like you said, a primary node, and then you have replicas. And in Spring Boot application, in Spring, where you have Spring Data, one option is to use that abstract routing data source, and based on the fact that your transaction annotation has a read-only flag or not, the transaction can be routed to either the primary node or to the replica nodes. So the read-only transactions go to replicas, the read-write transactions go to the primary node. In the context of what you have shown us, with those 3 nodes? Is this going to be transparent? So basically, I have the driver and I connect, and then the query or the statements are being routed on every node. Every node basically is both a primary and also a replica, right? It's a primary for some records, and because it's a cluster, right? So data being automatically sharded. Every node in the same time is both
a reader and a writer.
A reader and a write, because even if it fails, it doesn't matter, because data is automatically it has been sharded across the cluster. So I think that's better, because you can basically connect to any node, right? You can connect to any node and you are going to have the data.
Yeah, if let's say to give you an example, let's say that the database stores your bank account in one shard on node 1, and my bank account in another shard on node 2, right? So what happens here? Let's say your bank account is here. All of the requests to your bank account, like updates, selects, inserts, they will go to this node.
All right.
Because it keeps the primary copy of your data, of your bank account. However, you have backup copies of this data on the other 2 nodes. For instance, node number 2 and node number 3, they also keep the backup copy, consistent copy of your bank account. What it means, whenever your application sends an update request, the update request again goes to this node eventually, and that node will replicate this change to the other 2 nodes using Raft consensus protocol. But how this all stuff gets load balanced from the, let's say, data distribution perspective, then the application will decide to update my account, to request my account. That request will be handled by the second node that keeps the primary copy of the data. We do have, let's say, the notion, we do have true read replicas. It's like a standalone node that you would deploy, let's say, in a distant location, and that read replica node would receive changes from the from the standard nodes, right? Using the asynchronous protocol. It's like asynchronously. And I think in your Hibernate and Spring Data applications, you also can, let's say, use read replica nodes for read-only transactions if you can accept the stale data. Also, just I don't want to dump a lot of details. In this example, when your primary record is on the first node, but the backup record is on the third node, we have the notion of follower reads. Follower read, meaning that you can allow reads even not from the primary record holders. It's like, if you, let's say, your application connects to the node number 3 and you enable that special flag, allow follower read, then the application will be able to run read requests and serve your record from the third node and not from the first one. So there are several optimizations, but you're right. By default, every node is both a reader and writer.
Thank you very much for answering the question. We have another one from Ranganath. I need to check if Yugabyte can be connected via Hibernate and Atomicos. Now, in relation to Hibernate, I already showed you. So this demonstration that I showed you, they work automatically from Hibernate. I mean, what I showed you in the last example, 1 second to share my screen again. So in this, if you remember this use case here, as you can see, this is doing JPA and I'm using Entity Manager. But in your question, you also mentioned Atomicos. Now, Atomicos basically is for global transaction, for JTA transactions. And what I have showed you, and also the example, most likely that the example that Denis was using, they are basically using those resource local transactions, and the transactions are being managed via the JDBC connection object, calling commit and calling rollback on them. Now, do you know, Denis, there is something like XA resource data source. Is it possible to use a JTA transaction manager for Yugabyte? I mean, Postgres has that.
Yeah, I think that I don't see any YugabyteDB specific integration for Atomicos, which means that you are good to go with the Postgres implementation. So what Vlad, you did today, you used pgadmin, right? And pgadmin used the standard
yes,
drivers.
of course.
Same there, folks. Just try it out, the Postgres integration of Postgres driver. and my guess that everything would be running normally. If you face any issues, just go to our Slack community and we can discuss.
Thank you very much for taking one more thing related to this last question is the fact that in the context of Spring 6 and Hibernate 6, which migrated to Jakarta persistence, I know that in this repository I also have some JTA tests, and I had to switch from Atomicos to Narayana because currently only Narayana has support for Jakarta persistence. All the other JT transaction managers, I used to use Bitronics, which is no longer support, it's no longer maintained. But even Atomicos, I think that maybe it's going to take some time until they fully migrate to Jakarta persistence because the packages have changed. So also keep that in mind.
Excellent point.
Yeah, it's going to be a very interesting migration. Because there are a lot of things. It's not just basically the fact that you have to change yourself the package names, because all your entities are now going to be Jakarta persistence, not Javax persistence. But the thing is that every dependency that you've been using has to do the same. And if there is only one dependency who hasn't done that, that's going to be the point of failure for this migration in your case. So it's going to be interesting.
And there is a message from Ranganath who says Atomicos is not using Jakarta.
Yeah, they have an open issue for it, but it's still open. It's not fixed. I checked it and it's but then I switching to Narayana from JBoss. It was basically very easy. It took me like 5 minutes. Yeah, of course it was just for this repository, which is basically based on, it only has integration tests, but for some other application, probably it's going to be probably going to take longer. So I think that we can cover it. If there are any other questions, please let us know. We're also sorry for not having able to start at 0-0. But there was some technical problem, but luckily we managed to get it through.
We finished almost on time.
Yes.
Yeah,
that's why
we rushed it through. As you said, like when we were designing this session, Vlad kind of came, hey, like, come on, let's just do one hour presentation. I mean, we will manage to fit it, and he was actually right, because we managed to fit everything almost in 1 hour. But my kind of take was, hey, let's make it a little bit longer. Who knows, like, what might happen? We might need more time. And yeah, it's like something happened in the beginning, but eventually.
Next time we'll make it 4 hours to make sure that we'll fit in 1 hour for half a day. So there's another question from Ranganath about what cloud services are providing Yugabyte, or basically where probably you can run Yugabyte. On which cloud
Yugabyte,
you can run.
You can run it whenever you like. It's an open source. You can take it. You can run it on any public or private cloud provider. When it comes, if you're asking about the managed services, DBaaS, right, database as a service, then we support right now AWS and Google Cloud Platform, and the Microsoft Azure support is coming. So you just search for, if you're looking for managed service experience, just search for YugabyteDB managed. So you will get to our cloud portal and you can quickly start a database cluster whenever you need. So right now, AWS and Google, Microsoft, and I think Oracle a bit later. All right.
Okay. So I don't think we have any other question being asked. I'm not sure if we also had questions on LinkedIn. Because I didn't.
No, I think I confused everyone. Like, my thinking was that also this session will that it would be streamed to LinkedIn, but it looks like I confused everybody, including myself.
Okay.
Yep. Anyway, thanks everyone who stayed late and or who kind of waited for those first 15 minutes, just this session to start. Hope that you enjoyed this training. Hope that you enjoyed this presentation. So thanks a lot to you, Vlad, for the hardcore
too.
start and the hardcore conversation. And any other questions about, if you have any questions about Spring Data, Hibernate, databases, you know whom to direct them to. So that's Vlad. If you have anything related to YugabyteDB, then join our Slack community. We have a lot of database practitioners there. I hope that, Vlad, you also should join that community, because right now you are already can be considered as an very experienced guy in Yugabyte.
I have my 2 cents of knowledge in Yugabyte now.
Yeah, it's like you could already share.
Or 3 cents.
3 cents, 5. Okay, let it be 5. After this training, it's at least 5.
Adjusted for inflation.
Yep. And okay, the final question, and we're stopping this session. Is YugabyteDB open source? Yes, it's open source. It's licensed under the Apache 2.0, completely free, available on GitHub. Go and take it. If you want to compile it, you can compile it, but probably I wouldn't do that. So enjoy your day, enjoy your evening, night,
Thank you very much.
Morning.
Enjoy.
Yep. Thanks for joining us.
Thanks for participating, and have a great day, everyone. Take care.